The first spacecraft to visit Jupiter were the Pioneer spacecraft, and they really were very rudimentary things. This was the early 70s. And so they were very, very rudimentary. They weren't very, very detailed. They got the first pictures there. They measured some of the radiation environment, which was kind of a shock how intense it was. The Voyagers were much more capable spacecraft, and they returned a lot more data, a lot more detailed data, better images, and more importantly, much more precise other kinds of data, spectral data, and so forth. One of the odd things is Jupiter's thermal profile. So what we've got here is a graph of intensity on the vertical axis and wavelength on the horizontal axis. Now this is, remember Wien's law, it says that the peak intensity wavelength given off is related to the temperature. And so what we got here is we've got we've got here the graph, and this are wavelengths here given off. Now these wavelengths are quite long wavelengths, so that means that this is visual light over here, but down here this is infrared. Okay, and so what we want to do is figure out, well, what kind of wavelengths we're talking about. Well, the yellow line here is the sunlight hitting it. That's the spectrum of the sun. And you notice the spectrum coming off of Jupiter is like a miniature version of the spectrum of the sun. So that means Jupiter reflects some of the light that hits it. And actually it reflects quite a lot of the light that hits it. Those clouds are pretty bright. And so Jupiter does reflect a whole bunch of the light that hits it. And so that's why Jupiter looks really bright in the sky. This other peak over here is light given off by Jupiter. And so that's what's emitted due to Jupiter's temperature. And so you could find the peak of that and use that to calculate the temperature of Jupiter. Okay, now in physics, though, the intensity and the wavelength are related. If you take the integral, this is in calculus, you take the integral of the intensity over the wavelength, integral of the intensity, d lambda, then what that gives you is the area under this curve. Okay, now the thing is the area under the curve is of intensity per wavelength is related to the total energy output. Okay, and so or the total power output, total energy per second. So the area under that curve should be the same as the area under this curve. The area under the yellow curve is the power per second, or the energy per second going into Jupiter from the sun. The area under that purple curve, on the other hand, is the energy per second given off by Jupiter. Now, on Earth and all the other planets, those two numbers, the area under one curve and the area under the other curve, should be the same. That means that you're giving off the same amount of energy that you're getting from the sun. If you're giving off more energy than you're getting from the sun, you're cooling off. If you're giving off less energy than you're getting from the sun, you're warming up. Giving off the same energy you get from the sun, you're maintaining constant temperature. Well, clearly, the area under the purple curve, the total purple curve, is more than the area under the yellow dashed curve. That means that Jupiter is giving off more energy than it gets from the sun. It's like almost twice as much energy as it gets from the sun. So that was a huge shock right there, that Jupiter is giving off more energy than it gets from the sun. And so that means something has to be generating heat on the interior of Jupiter. Otherwise, it would have cooled off. Jupiter's been there for as long as the Earth has been here. Earth has been here for about 4.5 billion years. Jupiter would have been out there for at least 4.5 billion years. It may be a little bit more because Jupiter may have formed first in the solar system. Big thing, a lot of gravity, pull itself together fast. So Jupiter may have been even older. Now, that means, though, that it's been around long enough, it should have cooled off. It's not just leftover heat from formation. Something has to be generating heat in the interior. Well, what's going on? Like I said, it gives off almost twice as much energy as it gets from the sun. So how do you generate heat? Well, it turns out that even way before this, 100 years earlier, physicists had come up with an idea for how a large object can generate heat. It is something called Kelvin-Helmholtz Contraction. The idea is that we have a big ball of gas here, and this big ball of gas, under its own gravity, pulls itself together. You squeeze the gas. Now, what happens when you squeeze a gas? You squeeze a gas, it gets hot. When it gets hot, it tries to expand. It tries to push outwards. That balances the inward pull of gravity, and so it stabilizes. Well, that means, though, that it's warmer than it otherwise would be because it heated up a little bit by squeezing, and so now it's got to radiate energy off into space because that means it's not as cool as the surroundings, so it radiates energy into space. If you radiate energy into space, you cool off. So it cools off a little bit, and now it's not quite as outward pressure in the middle to overcome gravity, and so it ends up squeezing inwards just a little bit more. So it squeezes inwards a little bit more, which heats up the interior more, which pushes outwards more, which balances it. So this is Kelvin-Helmholtz contraction. And for a small object, it can only do Kelvin-Helmholtz contraction for a short amount of time. For a really big object, it can do it for a short amount of time because it squeezes itself down. But Jupiter is at just the right size that Jupiter can continue doing Kelvin-Helmholtz contraction for several billion years. Well, it's several billion years old. And it turns out that it is still finishing up Kelvin-Helmholtz contraction. So it all formed at the beginning of the solar system, and it's still collapsing on the inside, squeezing and generating heat from that process. And so that is why it's radiating more energy than it gets from the sun.